Let's start our today's class with a review of what we talked about in a previous session. So in previous session, we talked about Darcy-Weisbach equation that is used to calculate pipe head loss or major head loss. And I have written Darcy-Weisbach equation for you on this slide over here. F is friction factor, L is the length of the pipe, D is the diameter of the pipe, V is velocity, and G is acceleration due to gravity. Now, one variable that is very important to be able to find in Darcy-Weisbach equation is F, or friction factor. F depends on classification of flow, meaning that if flow is laminar, F is going to be calculated differently from turbulent flow. So just to classify it for you, let's start from laminar flow. If flow is laminar, in other words, if Reynolds number for pipe diameter D is less than or equal to 2000, then F, or friction factor, depends only on Reynolds number. However, if flow is turbulent, meaning that Reynolds number for diameter D is larger than or equal to 3000, then F should be calculated from Moody diagram or from empirical equations. What we're going to do today, and actually you will see here that I have Moody diagram for you. I gave you a quick introduction about Moody diagram in previous session. In this session, what I'm going to do is talk about Moody diagram in details and then talk about the equations that you can use. So this would be our today's agenda, to understand Moody diagram and understand equations that we can use to calculate friction factor for turbulent flow. In previous session, I introduced you to Moody diagram, and I told you that whenever you are going to use Darcy-Weisbach equation in order to find friction factor F, what you need to do is very simple. You need to use Moody diagram, and based on the relative roughness on the right-hand side y-axis, and based on Reynolds number, you'll be able to find the value of small f, or friction factor, to be used in Darcy-Weisbach equation. Now, in this session, I'm going to start with talking about characteristics of Moody diagram first. So you might remember this figure. What this figure tells you is that whenever you have turbulent regime, the flow has three different sublayers or regions. The flow around the walls of the pipe is viscous and very layered and smooth, so it's called laminar sublayer or viscous sublayer. The flow in the middle of the pipe is turbulent, which is characterized by the existence of different eddies, different basically turbulence in this region. Okay, and there is a transitional region in between the two. Why is it called transitional region? So if you are looking at the word transitional literally, it means that the flow basically changes from viscous to turbulent, from laminar to turbulent. However, there's another reason that it's called transitional as well. The characteristics of the flow at the transitional region, first of all, let me tell you that the transitional region is very, very small. So the characteristics of the flow in that region are not well known, because flow is very unpredictable. You cannot predict how the flow is going to basically behave in that very, very thin region. So what I'm going to do in this slide, I'm going to actually zoom in this and sketch this part of the pipe for you. Okay, so I'm going to sketch this part of the pipe over here. This would be the wall of the pipe. I'm going to hatch it right like this. And then you will have the velocity V or U, whatever you prefer, over here. And obviously there are eddies over here. Let me change the color to show the eddies. There will be eddies, and usually the symbol that we use to indicate eddies is something like that. And these are called eddies. So now let's go through the items one by one. Eddies indicate turbulence, and turbulence happens usually when the flow is developed in the middle section of the pipe. Okay. Number two says that there are eddies far from the wall pipe. Also, you know why? Because eddies happen in the turbulent flow region of the pipe. Now, number 3 says that at the pipe wall, there is a no-slip boundary. No-slip boundary. This is very beautiful. Now you see, and I think it was in the second class of this Engineering 368, and I introduced you to the fundamentals of no-slip boundary. No-slip boundary means that whenever you have a particle very, very, very close to the walls of the flow, the velocity of this particle, the instantaneous velocity, I'm going to call it u0, is equal to 0, right? So item 3 says that at the pipe walls there is a no-slip boundary condition. If velocity is 0 at the walls, it means no eddies reach the wall. So understandably, if the velocity very close to the wall is 0, eddies actually have a turbulent velocity. So it means that they cannot reach that region. Okay, and this leads me to another point, to another zone, I should say. There is a zone near the wall of the eddy, near the wall, that eddies cannot penetrate. That zone is called laminar layer or laminar sublayer or viscous layer. So there will be a zone over here. I'm going to show it by dashed green line, that eddies cannot penetrate into that. This thin zone is called laminar zone, or laminar region, or viscous region, or viscous sublayer, depending on what textbook, what scientific article you're looking at. They can have different names, but viscous and laminar are usually common in between all of these terminology that we usually use. Okay, and then finally, item number 6 says that if the Reynolds number is larger, the turbulent eddies are stronger and can get closer to the walls. So the laminar layer is thinner. It's very important that the laminar layer is dynamic. What does that mean? It means that it can go up or down depending on your flow rate. So if you have a very, very large flow rate, the eddies are going to be very large and they can penetrate into the laminar layer and push it down, okay? But if you have a small flow rate, this laminar layer can get larger and larger. So important to note that the laminar layer is dynamic. Now, in the next slide, I'm going to introduce roughness elements into my sketch to see how these layers interact with the roughness, the actual microscopic roughness of the pipe walls. In this slide, I'm going to show you the roughness elements. So I'm going to actually do the same pipe over here. This is a pipe wall. This time, this scale is microscopic. What do I mean by that? It means that it is very, very, very zoomed in, so you can see the roughness of the pipe. And I'm going to actually represent the roughness elements of the pipe by triangles like this. Okay, so again, just to recap, these two are roughness elements. Perfect. Now, whenever you have a weak turbulence, let's say that you have the flow rate over here and the flow rate is Q, and you have weak turbulence, and turbulence basically is indicated by eddies, so these are my eddies. Because these eddies are weak, the eddies cannot penetrate into the laminar layer, and basically these roughness elements are covered by the laminar layer. So I'm going to say roughness elements are covered by laminar layer. Perfect. So the eddies do not penetrate, or the roughness elements do not feel the impacts of eddies on them. Okay. This makes you feel that the flow is smoother when it's flowing in the pipe. Okay. Now let's take a look at another example in which we have simply strong turbulence. So again, I'm going to sketch the same wall pipe, and remember that the scale is microscopic, so it's very, very small. Now this time I have a stronger flow, Q, and also I have stronger eddies. And these are eddies. So as you can see, because the flow is stronger, the eddies are stronger, flow is more turbulent, the turbulence of flow is strong, the roughness elements can stick out of the laminar layer and can feel the impact of turbulence. So in this case, the laminar layer will be pushed down over here, So this distance would be my laminar layer, which is pushed down because the turbulence is stronger. And if you want to think about the physical process that creates these eddies, when you have stronger Q, when you have stronger turbulence, means that basically when you have a flow separation like this over here, and there will be small eddies, small wakes, I want to say, small wakes as a result of the flow separation over here and over here. And these wakes cause the laminar layer to go down, and as a result of that, the turbulence region is wider. Okay, so now to recap what I just said over here, I have provided you with a table. So when we have weak turbulence, the laminar layer is going to be thicker, and the roughness element is not exposed at all. So not at all. And the flow feels smooth. So the flow feels like that you have smooth walls. Now, when the turbulence getting stronger, then the laminar layer getting thinner, and the roughness elements, some of the roughness element is exposed, and flow feels some roughness. And eventually, when you have a very, very strong turbulence, then your laminar layer is going to be very thin. That was not a good color that I chose. Very thin. I'm going to change it to something else. And then the roughness element is going to be almost entirely exposed. And finally, flow feels full roughness. Okay, so it is important to have a good visual understanding of what is going on. When we are talking about turbulence, strong turbulence, weak turbulence, moderate turbulence, what we are talking about. So whenever we are talking about turbulence, think about the turbulent region and laminar region and how they are going to actually impact each other. And remember that the section that I sketched for you on this slide is very, very small. It's microscopic. Now we are going to take a look at the Moody diagram, and I'm going to tell you how you can visualize what I just told you in the previous two slides on Moody diagram. So first of all, it's important to realize that on the Moody diagram, on x-axis, we have Reynolds number. And the Reynolds number tells you about how weak or how strong turbulence is, right? When Reynolds number is low, turbulence is weaker. When Reynolds number is higher, turbulence is higher as well. So it is important to first of all notice this line over here, this straight line that we have over here up to this point. So if I go down over here, you will see that Reynolds number is 2000, right? This is 2000. And if you remember, when Reynolds number is less than equal to 1000, flow is laminar. And that line represents laminar flow. Okay. Now, in between that, between 2000 and 3000 or around 4000, we have transitional flow, right? So in between over here, this area that I'm going over right now, something over here, in this area, let me show it to you over here, this area, which is Reynolds number between 2000 to almost 4000, this is the transitional flow. We do not have any specific equation or chart in order to find friction factor for transitional flow. Why? Because this transitional flow layer is so thin that we don't even bother to calculate friction factor for transitional flow, because it doesn't usually happen and it's so thin we don't calculate friction factor for that. And then the rest from here, as you can see, when your Reynolds number is almost 3000, all the way to the end of this axis, here's when you have your turbulent flow. However, depending on where the location is, your turbulent flow can be stronger or it could be weaker, right? So this dashed line that I'm going over right now, and you can see this dashed line all the way up to here, this any point that is after that dashed line is called fully rough turbulent flow. Okay? Now, I want you to take a look at, let's imagine that our Reynolds number is 10 to the power 8 over here. So this is our Reynolds number. Now, every single change, in every small and slight change in relative roughness of the pipe can make a huge difference in frictional factor. What do I mean by that? Let's say that we have one pipe and relative roughness of the pipe is 0.001, exactly this point. Now, and let's say that we slightly, just a little bit, increase the roughness of the pipe to 0.002, which is this point over here. So now, if I want to find the friction factor for these 2 points, I just need to go in this direction to y-axis and then go in this direction again. So as you can see, every very, very small increase in the relative roughness can result in a huge difference in friction factor, large difference. And that's why when your turbulence is strong, which is here, pipe roughness can be felt. Now, let's see, what if the turbulence is weak, as we saw in previous slide? So if the turbulence is weak, meaning that Reynolds number is in area like here, in this area, right? For example, you can see the lines are very close to each other. Take a look at the 2 lines, for example, this line and this line. If you continue these 2 lines, you will see that when the flow is weak, these 2 lines are almost exactly the same. So if I want to find friction factor for this Reynolds number, they're basically the same thing. So this is telling me that whenever Reynolds number is in the lower spectrum of turbulent flow, whenever your turbulence is weak, friction factor between pipes of different relative roughness is not going to be way different. However, when turbulence is strong, in other words, when your Reynolds number is way high, even a slight change in relative roughness is going to change the friction factor by a lot. Okay, and this is basically the visual understanding that you can get from what I told you in the last slides. Now, there are a couple of other things that I want you to notice. There is one line, which is the last line of the Moody diagram, that represents smooth pipe. So whenever in a problem you have been given a smooth pipe, which could be a glass pipe or a plastic pipe, you are going to consider the smooth pipe and use the last line in the Moody diagram to find your friction factor. Another thing, as I told you, is the fully rough turbulent area. So this dashed line that I showed you before, or let me go over it once more, this line, dashed line, is the threshold for fully rough turbulent flow. How we're going to use this in future, you'll see that I'm going to show you some examples that understanding the region of the flow, fully rough turbulent flow, is going to be important. Now, what I want you to do after I'm done talking about this is to take a look at Moody diagram and understand how strong turbulence and weak turbulence is going to impact the value of friction factor. To complement our previous slide, let's recap some very important points. So number 1 says that at smaller Reynolds number, rough pipes have similar F as smooth pipes. In other words, roughness elements are covered. So what it says is that at smaller Reynolds number, so this region, for example, represents a smaller Reynolds number, rough pipes have similar F as smooth pipes. Let's take a look. Let's select the roughness actually. I'm going to select this 0.001 and go actually until intersection with that Reynolds number. There we go. Over here. So at this point would be the point for a pipe with this roughness. Now take a look at the smooth pipeline. This is the line for a smooth pipeline. If I go over it with purple, you will see that it gets very close to that point. So basically, for a small Reynolds number, F is going to be similar as smooth pipes. Why? Because as I told you, roughness elements are covered. Next, now we know that at moderate Reynolds numbers, F varies with both Reynolds number and roughness. And this moderate Reynolds number is called transitionally rough turbulent flow. So it's a subdivision of turbulent flow. It's called transitionally rough turbulent flow. Let me actually clean the Moody diagram to show you what it means. So, well, if your Reynolds number is moderate, somewhere over here, for example, then when you go up, there is a gap between these two lines, for example. So it's obvious that F changes with different values of relative, friction, right? Also, again, because this line in the transitionally rough turbulent flow region is curved, if you change the Reynolds number a little bit more, like over here, you will see that the lines are right now over the intersections are over here and over here, which are a little bit different. So you will get a different value of F, right? So in this region, which is called transitionally turbulent flow, F varies with both the Reynolds number and roughness. Now, where is that region? If you want to show it in Moody diagram, how do I show it? Let me actually clean this a little bit to be able to show the transitionally rough turbulent flow region. So the line that I'm going over with my blue marker is for smooth pipe, the last line in the Moody diagram. Now there is a blue dashed line that I'm going over right now with red dashed line, like this. If you read this, it says that this is fully rough turbulent flow. So anything on the right hand side of this red line is fully rough turbulent flow. Anything on this smooth pipeline is smooth. So the region in between the two, this region, in which the Reynolds number lines are almost curved for the most part, this part is called transitionally rough turbulent flow. The flow is still turbulent, but it's transitionally rough. It's something between smooth and full turbulent flow, okay? And that leads me to point number 3. For very high Reynolds, the roughness elements, I'm going to write it over here, so the roughness elements are fully exposed to the turbulence. So increasing Reynolds number even more does not change F or friction factor. This, as I told you a couple of seconds before, it's called fully rough turbulent flow. Again, let me show it to you on this Moody, beautiful Moody diagram. Okay, so again, this dashed red line is my fully, as it says over here, it represents anything on the right hand side of this dashed line represents fully rough turbulent flow. Okay, now what does that mean? It means that if you have a Reynolds number of, let's say, 2 times 10 to the power 7, okay, and if you have the relative roughness of 0.002, this line is almost a line, is almost a straight line. Okay, so it doesn't matter if your basically F value would be over here, right? Be 0.025. Now, if I increase the Reynolds number to 6, change the color to purple, so to 6. Again, I go up. Because the green is a line, a straight line, again, my F is going to be the same value. Now, if I increase it to basically value of 4, decrease it to the value of 4 over here. Again, when I go up, the intersection is with a line, so again, it would be the same value. This region, anything on the right-hand side of the dashed red line, is called fully rough turbulent flow. And the main characteristic of that is that increasing Reynolds even more does not change the value of F. So F only changes with different values of relative roughness. Okay. Now, and point number 4 is that fully rough turbulent flow is the region to the right of the dashed blue line. In this case, I went over it with my dashed red line over here. Okay. So now you have a good understanding of different regions and different basically classes of turbulent flow that you can find them on the Moody diagram, and you should be able to understand the shape of Moody diagram. You should be able to understand why these lines are flat or they're curved, or why are they going up and coming together, or why are they going to the right hand side and there's a gap between them. I am pretty sure that by now you have a question in your mind. Are there any equations that we can calculate friction factor based off? Or should we go to Moody diagram every time and calculate friction factor, or basically find friction factor on Moody diagram? The answer to that would be there are empirical equations that are developed based on different experiments and based on Moody diagram. Multiple empirical equations. However, in this class, as I have written over here, we are going to read F, or friction factor, based off Moody diagram every time, unless you are told otherwise in the problem statement. The reason that we like Moody diagram a lot because it gives us insight into the pipe condition. As I described to you, different regions of Moody diagram have different meanings, and it's important for you as engineers to be able to understand the meaning behind every region and how turbulence is going to impact friction in our pipes. So I want you to spend a lot of time on Moody diagram and make sure that you are mastering Moody diagram and how you read data from it. However, I'm going to introduce you to different equations as well. One of the most famous equations to calculate friction factor is called Colebrook equation. Colebrook equation that I have written for you over here, as you can see, there are F, or friction factor, on both sides of the equation. So there are no explicit answer to this equation, and you need some type of iteration to find F for this, to find F based on this equation. This will be used for computer softwares or computer codes when you are assigned to find F. Because obviously when you are coding, you cannot tell the code to read the diagram, so you need to use an equation. Swamy and Jain based on Colebrook equation, they came up with an explicit version of Colebrook equation, and they call it Swamy and Jain equation, which is over here. So as you can see, F is only on the left-hand side of the equation, and on the right-hand side of the equation, you have Reynolds number for the pipe, and also you have relative roughness over here. This is relative roughness, right? So based on Reynolds number and relative roughness, you can directly calculate the value for F, which would be very similar to Moody's diagram. They're not exactly the same, but very similar. If you take a look at other textbooks and scientific papers, you will see that there are multiple other equations that you can use to calculate F. I just introduced you to two of them. Another famous one that water resources engineers use to design pipelines and irrigation and sprinkler systems is an empirical equation called Hazen and Williams. Hazen and Williams is very common in water resources engineering as well. Now, we're going to take a look at an example to make sure everything makes sense and you are familiar with how to use these equations. Let's take a look at a practical example. In this example, we have a 6 inches diameter galvanized iron pipe that transports water at the temperature of 100 degrees Fahrenheit. What we're going to find is head loss, HF, and pressure drop, or delta P, in 200 feet of the pipe that carries 400 gallons per minute flow rate. Now, we have been asked to use both Moody diagram and Swamy and Jain formula. So in this slide, I'm going to use Swamy and Jain formula, which has been given over here. And I told you about it in previous slide as well. The first thing that we need to do is to calculate Reynolds number to understand if the flow is turbulent or laminar. And you already know that Reynolds number can be calculated using this formula: velocity, diameter, and kinematic viscosity. But we do not have the value for velocity, right? So we should calculate the value for velocity, which is equal to flow rate divided by cross-sectional area of the pipe. So what I am going to do is to plug in flow rate over here, and notice that flow rate is 400 gallons per minute, or GPM. So we need to convert that to cubic feet per second. In order to do that, I'm going to write down 1 minute is 60 seconds, and then I need to calculate gallons to cubic feet as well. So it would be 1 cubic feet is equal to 7.48 gallon. This is how to convert it to cubic feet per second. And also the denominator is the area, which would be pi divided by 4 diameter, which is 6 inches, divided by 12 to be feet, to the power 2. Perfect. So when you calculate this value for velocity, would be equal to 4.539 feet per second. This is the velocity. Now we need to calculate Reynolds number based on the value of velocity. So Reynolds number is equal to 4.539 feet per second times the diameter is 6/12, and viscosity of our water at this temperature. You need to go to table A5 of your book and find the kinematic viscosity for that temperature. I've already done it, and the value is 7.39 times 10 to the power -6 with the units of squared feet per seconds. So eventually your Reynolds number will be 3.07 times 10 to the power 5. Now, if you notice, this value is larger than 3,000, and as a result, our flow is turbulent. Perfect. So now we know that the flow is turbulent. What we are going to do is to calculate F, or friction factor, for turbulent flow. What I'm going to do is use Swami and Jain formula on this slide, and then on the next slide I will use Moody diagram. So let's use Swami and Jain formula over here. For Swami and Jain formula, as you can see over here, we need the sand equivalent roughness. So you need to go, let me remove this part over here. You need to go to table 10.4 and find K sub S for galvanized iron, which is the value of 0.006 inches. Perfect. Now, I'm going to calculate relative roughness, which is K sub S divided by diameter. It would be equal to 0.006. Remember that this is in inches, so I need to divide it by 12 to be in feet. And then diameter is also 6 inches divided by 12. So this value also would be in feet as well. K sub S over D would be 0.001. Perfect. So now I just basically calculated K sub S over D over here. All right, now let's write down Swami and Jain equation. F can be calculated based on Swami and Jain equation. We have log 0.001, we just calculated, divided by 3.7 plus 5.74 divided by Reynolds number was 3.07 times 10 to the power 5 to the power 0.9, and the entire thing is to the power 2. So when you calculate this, the value for F would be equal to 0.0207, and this is the friction factor. Fantastic. So now we know that we have a length of 200 feet of this pipe, and we want to calculate head loss and pressure drop. Head loss is easy to calculate. I am going to do it over here. Head loss is equal to F, length of the pipe, diameter of the pipe, velocity to the power 2 divided by 2g. So if I plug in all the numbers over here, it would be 0.0207, 200 feet, 0.5 feet the diameter. Velocity is, where did I calculate velocity? It's 4.539 to the power 2 divided by 2 times 32.2. So as a result of that, HL is equal to 2.66 meters. This is the head loss. Now, we calculated head loss as we were asked. We need to find the pressure drop. The equation that can give us pressure drop, or delta P, is energy equation. So what I'm going to do is write energy equation. Energy equation for section 1, or inlet, section 2, outlet. I'm going to write down the full form of energy equation. So pressure N divided by gamma plus Z N plus velocity N to the power 2 divided by 2G plus HP, which is representative of any pump if we have it in the system. And then the same thing for the outlet. HL. All right, let's see how we can simplify this equation. We know that because the pipe is horizontal, these cancel each other out. There is no pump, so this is 0. There is no turbine, so this is 0. And now what we basically have in this equation is velocities in and out and pressures in and out. And we already know that because the diameter of the pipe is the same thing, velocity and the flow rate is the same thing, so velocities will be equal. So velocities can cancel each other out. And as a result of that, simply from this equation, you can conclude that HL, or head loss that you calculated, is equal to delta P divided by gamma of water, right? And notice that gamma of water is equal to density of water at 100 degrees. This wasn't, let me rewrite it again. At 100 degrees Fahrenheit times G. So you need to find density of water at 100 degrees Fahrenheit. I've already done that. It is 1.927 slug divided by cubic feet times 32.2. So if you take this value that you calculate over here and put it inside this equation, and you already calculated HL, I will write the value of HL. I will write the value of delta P over here, which will be equal to 165.17 pounds per square feet, and this is the pressure drop. All right, so we calculated head loss and we calculated pressure drop. Remember that we calculated this pressure drop and head loss based on Swamy and Jain equation. Now, what I'm going to do, go to the next slide and find the value of F based on Moody diagram and see how it differs from Swamy and Jain equation F. All right, I just recapped the Reynolds number that we calculated in the previous slide and a relative roughness that we calculated in the previous slide, and F, or friction factor, from Swamy and Jain. Now, what we are going to do in this slide is, based on Reynolds number and relative roughness, calculate F, or find F from Moody diagram. So Reynolds number is 3.07 times 10 to the power 5. So first of all, I will find 10 to the power 5. It's over here. And then find 3. It would be between 2 and 4. So it's over here. That's the value of Reynolds number. Now I'm going to find relative roughness 0.001. It is over here, so I'm going to go over this line so it's clear for me where the line is. Now going to go up over here until the intersection between these two lines, these two green lines, which is over here. Now if I go to the left-hand side axis, it would be somewhere over here. All right, so the value is just a little bit over 0.020. I'm going to say it is 0.0209. And as you can see, the value is very close to the value that we calculated from Swamy and Jain. So if you go ahead and calculate head loss and pressure drop, realistically, these two values from Swamy and Jain and Moody diagram should be very similar to each other, because the value for friction factor are very similar to each other as well. Now I'm going to give you some strategy for solving problems related to pipe flow. There are 3 different cases when it comes to pipe flow problems. Case number 1 is when you are going to find HL or HF. Basically, when you are going to find head loss. In order to do that, you just need to find F, friction factor. You need to figure out if your flow is laminar or turbulent and use the correct diagram or correct equation to find F, and then substitute it in Darcy-Weisbach equation and find HL or HF. It's a very straightforward kind of problem. That's the easiest case that you can encounter, and there is no need for iteration at all. So the case 2, which is a little bit more complicated, is when your goal is to find flow rate, or Q. or pressure drop, delta P. So in this case, the pipe length, the pipe diameter has been given to you, and this type of problem usually requires some kind of iteration or iterative approach. And finally, case number 3, which is also called design case, is when your goal is to find pipe diameter. That's why it's called design, because you are designing pipe for a system. So whenever you are designing pipe diameter, usually flow rate is given, the length of the pipe is given, and the head loss is given as well, and you will be able to calculate pipe diameter based on an iterative approach as well. Okay, so we are going to go ahead and see some examples of these 3 cases. I'm going to start with case number 1, which is the easiest, and then next session I'll talk about case number 2 and case number 3. All right, let's take a look at example that explain case 1 type of the problems in pipe flow problems. Water at 20 degrees Celsius flows at a rate of 0.05 cubic meters per second in a 20 centimeter asphalted cast iron pipe. What is the head loss per kilometer of pipe? So obviously, because we are going to find head loss, or HL, this is type 1 or case 1 problem, and we don't need any iteration. So the way to solve this problem is exactly the approach that we took, for example, number 1 previously in this session. What you're going to do is, first of all, calculate Reynolds number, and Reynolds number requires you to have values for velocity, diameter, and nu or kinematic viscosity. We do not have value for velocity, so I'm going to go ahead and calculate velocity first. Velocity would be equal to Q divided by area, and we do have flow rate 0.05 cubic meters per second, and area would be pi over 4. Diameter would be 0.2 meters to the power 2, so velocity would be equal to 1.59 meters per second. All right, so this is our velocity. Now I can put the velocity into Reynolds equation and calculate Reynolds number for diameter D. 1.59 meters per second, 0.2 meters, and kinematic viscosity. You just need to go to table, I think it's A4 if I'm not mistaken, and calculate kinematic viscosity. I have it right in front of me. It's 10 to the power negative 6 meters squared divided by second. So Reynolds number is equal to 3.18 times 10 to the power 5. And obviously, because this number is larger than 3,000, then our flow is turbulent. So in order to find F to calculate HL, we need to use a Moody diagram, right? What I'm going to do is write down Ks over D, which is my relative roughness. So Ks over D, Ks for asphalted cast iron would be equal to 0.00012 meters, and it comes from table 10.4, and then diameter is obviously 0.2 meters, so this value, or relative roughness, would be equal to 0.0006. Now I have the Reynolds number, I have relative roughness. I need to go to Moody diagram, and based on Reynolds number of 3.18 times 10 to the power 5 and K sub S over D of 0.0006, if you find F, or friction factor, it would be equal to 0.019. And based on this, I can go to Darcy-Weisbach equation and write the equation. Length of the pipe is 1,000 meters. Diameter is 0.2 meters. Velocity I calculated to be 1.59 meters per second, should be to the power 2. And 2 times 9.81, and the unit for this is meter over squared seconds. So HF, or head loss, would be equal to 12.2 meters. Perfect. So over a pipe with a length of 1,000 meters, diameter of 0.2 meters, when water is 20 degrees Celsius and flow rate is 0.05 cubic meters per second, the head loss would be equal to 12.2 meters. And that's the case one type of problems that you might case. As you can see, it's not difficult. There is no iteration involved. It's very straightforward and explicit to find the value for head loss.